Hi everyone, welcome to Math Analysis, and this video is going to be talking about section 3.2, polynomials and their graphs. And this first video is going to be going through a lot of information and very little examples. I will do more videos with examples in them after, but we need to get through a lot of information first of all. And things like that. First of all, we have to get the definition of what a polynomial is. And you have seen polynomials already. We're just going to formalize what that definition looks like. So I've kind of written it here. It is in our textbook, so I kind of took it out of our textbook. But I kind of want to talk through it because, again, part of my job in this course is to get us better at mathematically reading something or reading something mathematical. So we have a definition for a polynomial, and first of all, it is a function. So we have to remember it will pass that vertical line test, and it's going to be of degree n. That's another definition piece that we'll see in this written work. It's going to be of the form. So again, here's our p. We're using p for polynomial just because, and it looks something like this. So we have a sub n x to the n, a sub n minus 1 x to the n minus 1, all the way down to a sub 1 x, and there would be like a first power here, and then a sub 0. Now, don't get hung up on the fact that all these little subscripts and powers. First of all, these are exponents just like we're used to. N is some non-integer, non-negative integer like 5, 7, or whatever. And we're going to have like x to the 5th, x to the 4th, x to the 3rd, and so on. We just wanted a way to label our coefficients or the numbers in front of them. So we use these little symbols. So a sub n is just a symbol. We do have that a sub n is not equal to 0 because we want that first one to be a non-zero term. All of these a sub n's are called coefficients. They're just numbers. So we're going to have just numbers in front of our powers of x. A sub 0, this one on the end, is sometimes referred to as the constant coefficient because it is the constant on that coefficient piece, or we just refer to the whole thing as that constant term. A sub n is going to be the leading coefficient because it's going to be leading the line of exponents, and it's going to be the value in front of your highest exponent. This whole piece is that leading term. Some examples that we've seen, or just some examples: 7x cubed plus 5x minus 3. There's an example of a third degree, so the highest power is going to be the degree of your polynomial. So 7x cubed, this would be a third degree polynomial. Some things that are not polynomials, so I'm going to kind of abbreviate polynomial there. Something that has a square root, that is not a polynomial. So our exponents on our x's have to first of all be positive. We can't have like x to the negative first. We can't have fractional exponents. We have to have integer exponents. So they make them a little bit nicer. Polynomials are nice functions. We have seen these guys before, our x to the n, sometimes referred to as our basic power functions. And I'm going to attempt to draw them. So we've seen, first of all, x to the 0. I'm not going to draw that one, but just simply x. Y equals x is your straight line, slope of 1, y-intercept at 0. We could have had x squared. I'm going to put that on this side. X squared is our parabola. And then we started introducing other ones as well. We have x cubed. If I can draw this. That looks bad. X cubed, x to the 5th, x to the 7th will all have that S shape. We talked about how they're going to get steeper on the ends, flatter in the middle. X to the 4th will be steeper and then flatter. Whoops. Boy, my graphs are bad. But there's x to the 4th. And we could do x to the 5th would look similar to these, x to the 6th, and so forth. And if you can remember, when we looked at these in Chapter 2, we learned how to shift them. So let's go ahead and remember that. So let's look at this guy and remind ourselves how we shift functions. So first thing we have to realize is this is our basic x to the 5th function. X to the 5th looks similar to x cubed, but a little flatter. Okay. Then again, we are going to be shifting it, so we have this -3 on the inside, we have a negative on the outside, we have a +2 on the very outside. Order of operations tells us to work inside, so we'll be dealing with that -3, which will shift it to the right 3 units. Remember, when we are on the inside, it works backwards. So instead of going left like you think you would, we're going to go to the right. This negative is on the outside, so it affects our y values. So it will flip this vertically. So along that x-axis. And then the +2 is going to shift it up 2 units. Okay. And when we did Chapter 2, we had some points, and we did these to the points. This one I'm going to just actually physically do, so we're going to kind of figure out what's going on. The first one is shifting it over 3. 1, 2, 3. So to kind of look, I'll put these in dotted. There it is, shifted over 3. Now we need to flip it. So I'm going to flip. Kind of make little X's. It's easier to make dotted. So that's flipping it. This is coming down here. This piece is going up there. And then we're going to go up 2 units. So it'll look something like that, roughly speaking. So there, remember, we can maneuver these polynomials up and down and left and right and all over the place. So don't forget all those things we learned in Chapter 2 on how to shift. We do want to talk a little bit, because our ultimate goal is going to be graphing these things without a graphing utility. We're going to look at some end behavior. What we mean by end behavior is what happens if we're looking at a graph. What's happening over here when x is going towards infinity, when x is going towards infinity, or x is going to negative infinity. If we have an even degree, so 2nd degree, 3rd, 4th degree, 6th degree, so n is 2, 4, 6, and so on. What happens will depend on our leading coefficient. And the thing is, if a is greater than 0, so our leading coefficient is positive, our function is going to go towards infinity as x goes to infinity. In other words, it's going to kind of do this up thing, this up arrow. So you'll have some things going, it'll get growing bigger and bigger and bigger. Also, as x goes to negative infinity, if we have an even, remember, think of your quadratic. The ends do the same thing, so they'll be going up. So it will also be going to infinity. So it'll kind of look like that. on the ends. If we have less than 0, it's going to be down here. It's basically flipping it upside down. P of x is going to go towards negative infinity as x goes to infinity, and as x goes to negative infinity. So they'll kind of have the ends that go down and go towards infinities. So you'll have a bunch of stuff going on in the middle. We have no idea what's happening there. We have to analyze things a little bit more in depth, but that's going to come. If we have an odd degree, so that's if it's an even, so the ends do the same thing. Either they're both going up or they're both going down, depending on that leading coefficient. If you have an odd degree, so if n is equal to 1 or 3 or 5 or 7, think of what those functions do. Look at your x, x cubed, x to the 5th. If your leading coefficient is positive, like x, x cubed, we will have this sort of thing going on. I like to think of it as it's coming from the basement, it's going to do some wiggles and squiggles in the middle, and then it's going to end up in the attic. And it's going to keep climbing. So this one keeps going, and it keeps climbing. So we could write this, P of x will go towards infinity as x goes to infinity, or it's going to go to negative infinity as x goes to negative infinity. Or it starts in the basement, does some wiggles and squiggles, goes up to infinity. If our leading coefficient was negative, that's like flipping it upside down. So it's going to start from the ceiling, do some wiggles and squiggles, and it's going to end up going into the basement. So P of x will go to negative infinity as x goes to infinity, or our P of x will go towards infinity as x goes to negative infinity. And we will keep all of these things in our minds when we are graphing our polynomials. We'll make sure we keep track of what's happening on the ends, and we'll be putting some more details on what happens in the middles. All right, some more information about polynomials. First of all, just some language that we're going to be seeing and how we discuss zeros. So a polynomial P is a polynomial, and we have some C, some real numbers. The following statements say the same thing in just different words. We can say that C is a real zero of P. So if I say C is a zero, that should mean something to you. It can tell you that x is equal to C is a solution to setting that polynomial equal to zero. So being a zero, being a solution, same thing. When we have polynomials, how we find solutions, a lot of times thinking of our quadratics. They are one specific polynomial. We try to factor them. And if we have x minus c as a factor, we'd set it equal to 0. X equals c would be that solution. So these all say the same thing. We have a factor, we have a solution, it's called a zero. And if we're graphing it, we graph the zeros as x-intercepts. So we'd have on our x-axis all those little dots where we had those zeros and so forth. And we saw this with quadratics. We're going to extend it to other polynomials. The hard part is going to come when we're trying to find all of these zeros or all of these solutions or all of these factors. They're not always going to come easily. One last theorem from this section. And I lied. Well, it is a theorem, and it's a pretty big one. This is called the intermediate value theorem. And it is very useful. It is used a lot of times in helping us find solutions because sometimes we can't do it mathematically. I mean, we can't do it algebraically, sorry. We can't do it algebraically. So what the intermediate value theorem tells us is if we have a polynomial, so some sort of polynomial, some polynomial degree, we don't care, and we have two y values. We have one y value and another y value, and they are opposite in sign. So one is positive and the other is negative. What this tells us is there exists at least one value c between a and b for which c is a 0. So, for example, I'm going to kind of draw a picture. So let's say we have, here's a and here's b. So two values. They could have been on the other side of the x-axis. They could have been one on one side of the x-axis, one on the other side of the y-axis. But I'm just putting them over here. They're somewhere on the x-axis. And I could have had them flipped around too. But a and b are on the x-axis. One of them is positive, the other is negative. So here's one positive, one negative. What the intermediate value theorem tells us is that we have a 0 somewhere in between there. And the reason for that is because polynomials are nice, smooth, non-breaking functions. They will go from one point to another point, crossing every value in between. So since we had to go from being positive to being negative, there has to be a 0 in here somewhere. We may have had more than one, because who says